Welcome to our next episode of Smart Control in Practice. I'm Jackson, the Analytics Lead at SIG Machine Learning. In our previous episode, we covered the topic of dynamic optimization and how a smart controller can enable more effective management and operation in a complex network of industrial assets. If you'd like to learn more about this topic, check out our YouTube video titled Dynamic Optimization. In this episode, we'll delve into the topic of emissions reduction and explain how a smart controller can assist with reducing the carbon footprint of industrial assets by running them more efficiently. Before diving in, let's explore how emissions reduction is integrated into our overall strategy for optimal asset management. Oftentimes when operating industrial assets, it's being done with competing strategic objectives. An example of this can be operating the asset to improve reliability and decrease emissions, all while ensuring production targets are not impacted. This is not a simple balance between two objectives, but rather an interplay between multiple objectives which can change on a day-to-day basis. So we might think of an operational strategy as a balance, but the reality might be something a little more complicated in practice. After all, we don't want to be always focusing on the relationship between two objectives at the cost of negating production from our asset. A smart controller is trying to optimize the system while balancing multiple objectives. And what is the strategic weighting for each asset? Well, this all depends on what the data is telling us at a given point in time. There may be little point in pushing a system too hard if it comes at the cost of both increasing our emissions and reducing our reliability. For an operating gas well, we have a physical limit to how much can be produced at a given point in time. This is primarily governed by the inflow potential of the reservoir that we're extracting fluid from. So running our pumps at speeds above its inflow potential can result in tons of additional carbon emissions that could have otherwise been avoided. Not to mention, when we run a system more efficiently, we are reducing the risk of the system failing by implementing preventative maintenance strategies into the way that we operate. Note the point on screen where the controller in place is continuing to increase pump speed in an attempt to increase production. We can see at this point water starts to level out, but the continual increases result in further incremental power consumption. Our counter in the top right corner has estimated an additional 0.3 tonnes of emissions that could have been avoided over a 40-day period. This might not seem like much, but what if we scale it up to 1,000 assets? Even if there's a small portion of the fleet that needs to be running more efficiently, the prevention of excess emissions can be quite significant. The cumulative effect over time is what we're interested in here. Minimising this impact helps us to operate in a more sustainable manner. To recap on our previous animations, using a smart controller to improve the system's efficiency can provide the following benefits. Cost reduction. By optimizing pump speed, we can lower electricity consumption. Additionally, this can also help to prevent failures that result from overworking the system, which can cause excessive wear and tear on equipment. Enhanced engineering efficiency and emissions reduction. By identifying and automating the actions required to optimize pump speeds, we can increase engineering efficiency and reduce emissions at the same time. Let's take a look at an example of an emissions reduction opportunity via our NextGeneer platform. The following trends are of an operating gas well. Each trend is showing us data from telemetry on site. To demonstrate this opportunity, we'll now need to focus on our production rates and pump speed. The smart controller is currently operating in open loop, meaning that recommendations are being generated in the swim lane below, and the engineer is responding to the recommendations by actioning them in the control system. There are two unique recommendations over time. Focusing on our swim lane below, these are decreased speed recommendations in blue and no action recommendations in grey. We can see the overall trend of water is naturally declining, suggesting the power requirement for the pump to produce this required rate is decreasing over time. Leading up to the offline period, the smart controller is already recommending to slow the pump down to match the inflow potential of the well. After the shut-in, the smart controller has recognised a constraint where the well has been shut in for an extended period and is generating no actions for a period of time until the system has stabilised. Once stabilised, speed decrease recommendations are being generated by the smart controller, which the engineer responds to by manually decreasing the speed of the pump. This is action 1 annotated on screen. The smart controller identifies no negative impact to water rate beyond the declining trajectory. This signals a period of decreased speed recommendations, which the engineer responds to several days later. Once again, there's no negative impact to the water rate, identifying that reducing the speed was also helpful in reducing the power requirement, without impacting production. This is annotated on screen as action 2. The smart controller has identified a period of stabilisation. The system is still being monitored for anomalies, but for now, the dynamic optimum has been registered by the controller and it is awaiting a further decline in water rate before any further speed decreases. This leads into action 3 on screen. The engineer attempts an increased speed step test to see if the water rate responds positively. There's no significant increase in water rate that's been measured. The smart controller then recommends rationalising the pump speed back to the previous speed, which has been noted to be the dynamic optimum. This demonstrates an example of how a smart control system can support engineers with both recommendations and after-action reviews of set point changes to help find the optimal pump speed, whereby reducing power consumption and increasing system reliability. If the smart controller were in closed-loop control, we'd see these changes occur autonomously. In our next video, we'll demonstrate and discuss how a smart controller manages system constraints. Until then, if you have any questions, please reach out to the team at SIG. Catch you next time.